Hello everyone, my name is Praveen Bhagwatula. So today I'm going to speak a little bit about the some of the SONiC enhancements that we've been looking at and leveraging on some of the work that was already done in the context of chassis, specifically for the ML and AI backend networks. So for those of you who have followed the recent OCP summit, there were a couple of talks around how does the scheduled fabric based models apply for the backend ML AI networks, the advantages that they bring to the table with respect to providing better load balancing, better congestion management, and improving the overall job completion times, as an example, for specifically for the backend network. So I'm going to pick off of that and essentially talk about, assuming that there's a well-established aspect of the benefits that it brings to the table. How do we take SONiC and some of the work that has already been done? What are some of the simplifications that help improving or rather simplifying the SONiC deployment in the context of the backend networks? And what are some of the design options that are being evaluated? And then, obviously we'll have to work with the community to kind of pick up what's the right design choice for this. All right. Okay. So why SONiC for the backend ML AI fabric, right? So first of all, obviously it has a wide range of deployment models, whether it's, someone wants to use standard ECMP, play with the enhanced Ethernet with, in-band telemetry assist, or scheduled fabric. SONiC is probably the only NOS and very well wide accepted from a data center fabric standpoint for all of these use cases. Some of the key components of the distributed control plane and scheduled fabric, they're already in place. The work that has been done over the last 3 to 4 years in the context of the chassis. And obviously the multi-vendor ecosystem, and now the same OS can become the SONiC can become the de facto OS both for the front-end networks and back-end networks. And one thing I wanted to point out that even though we have been talking about this primarily in the context of the backend networks, we believe there are additional applications outside of the pure MLAI workloads that can take advantage of these the scheduled fabric-based deployments in general in data center fabric environments. Okay, so just a quick recap before we jump into the disaggregated aspect of it from a SONiC on chassis standpoint, just a little primer on that. So the idea in terms of the high-level design was we take a chassis and break it up into a bunch of SONiC instances. Each line card runs its own SONiC instance. And then the RP, the route processor or the switch, the supervisor runs its own SONiC instance, which manages the chassis and the fabric elements. And each line card SONiC instance manages the ASICs or the NPUs on those line cards. And there is some amount of global state that gets distributed through configuration, things like system ports and so on. And there's also a bunch of state that is either exchanged through standard routing protocols like IBGP, especially when they want to exchange the external prefixes that are learned on each line card instance. And because of the convenience that a chassis brings in, where there is already a supervisor that is running SONiC, a very good design choice at that time for the chassis was to instantiate a chassis-wide database. And anything that is not traditionally exchanged through routing protocols can now be exchanged through the chassis DB. So for example, things like lag membership or things like remote neighbors and next hops, the DB that runs on the chassis has been a good model for exchanging that information. Now, if we take that model and adapt that, the SONiC chassis model and adapt that to a disaggregated scheduled fabric, there are a few simplifications that would be good to look at, especially in the context of the backend networks. For example, pretty much all of the communication is GPU to GPU. I'm using the term GPU to kind of represent the endpoint. It could be a smart NIC, it could be a CPU or a DPU, anything that gets essentially plugged into the CPU port. Because the workloads are running on the CPUs or the GPUs and they're exchanging the intermediate data, all of the communication is essentially GPU to GPU communication. It's host IP routing at the end of the day. There are no external prefixes that are induced into this network. There's no EBGPs here. There is no cross-leaf lag. In fact, there is no lags in the picture because every southbound port of the top of the rack connects directly into a server port, and on the northbound, it's all scheduled fabric with packet or cell-based sprays. Right. So that simplification actually comes handy when we look at the design choices. The other piece that's important to look and probably forms the crux of the conversation here is because now this is all disaggregated and every leaf and every spine is completely independent on its own. And keeping in mind and aligning with the standard data center design principles, the goal would be to avoid any sort of centralized control plane component. Because in a chassis, if the centralized component like the chassis DB fails, you can take the entire chassis out of the equation, but typically there is a lot of network level redundancy at those layers. Whereas in this model, if something that is centralized fails, then that entire cluster, it could be 4,000, 8,000, or 16,000 ports, that entire cluster would essentially be gone with that centralized model, right? And then the other piece which we have not touched a lot in the community, but one other thing that the fabric-based multicast, actually the scheduled fabric brings to the table is most of the ASICs that do support scheduled fabric also support inherent fabric multicast. And that could also be used in some of these cases for some of the control plane type of communication or establishing the state. So on the CPU to CPU communication, this is primarily needed for establishing any type of state. So this is like the step one of establishing any communication, whether it is BGP communication or any other database type of communication. And again, I'm just probably a little bit of a primer on this one also, but basically for the CPUs to talk to each other on the top of the racks, you need the IP plus MAC address and the VOQ on the system ports. IP address comes naturally as part of the session configuration. If you can, setting up IBGP sessions across, you already know that. The system port is already configured. MAC address, you could statically configure it, or because there is fabric multicast already in the picture, and we are talking about, a few hundreds of top of the racks here. It's not a significantly large scale by any means. The fabric multicast can essentially be used to resolve the ARPs and NDs if it's all V6. So without having a lot of static configuration, the CPU to CPU session can be established reasonably well or pretty simply in this model. Now, from the remote host IP distribution, and this is where each of the CPU port's IP address is known to the CPU to all the other top of the racks. As an example, in a chassis-based model, we would use the chassis DB for that. In fact, that's how the remote neighbor distribution and the next hop distribution is done today. In the case of disaggregated environment, if you want to completely eliminate the centralized models, there are couple of options that we have been discussing in general, and obviously as a community we need to come through and evaluate the pros and cons of these options and figure out which ones make sense. One is using a Redis replication or a Redis cluster model. Redis supports a couple of models, either the Sentinel model or the cluster model, where you could take up to 3 or 6 of these top of the racks and run the active and the standby instances of the chassis DB. Now, obviously, this model aligns better with the current chassis design because you're essentially taking the same design model and applying it in a distributed environment using the Redis cluster model. And once that is in place, the neighbor orcs or the orc agents would talk to the active chassis DB, and the Redis cluster does support a virtual IP address that represents the entire cluster. So from the application standpoint, they would always talk to that the virtual IP, and then Redis ensures that the connections actually go, or the requests actually go, and the response comes from the current active chassis DB. Now, while this model works, it also has a downside that now we're making a few of the top of the racks quote unquote special. So there is still, while it's not fully centralized, it's quasi-centralized in that approach because these top of the racks do become special entities and they need to be managed specifically or specially, right? The second option, which completely eliminates any aspect of centralization or reliance on a subset of top of the racks, is again relying on our everyone's favorite protocol, BGP. Now, for those of you, so most of you would already know that EVPN address family that was added to BGP several years ago does support a few new route types, specifically route type 2 as an example, which already carries IP plus MAC address, so that could be distributed through standard IBGP. Route type 2 also supports a few additional attributes that can be used to distribute system port, which is really the only other missing piece in the equation to establish a full IP-to-IP connectivity. FRR does support the EVPN address family, but there'll still be few extensions that are needed. And SONiC already supports the ability to inject routes into FRR directly without going through the Linux kernel stack. So we don't have to bother the kernel for or like having to have this knowledge. You can we'll use SONiC to BGP or SONiC to FRR communication path by enhancing the ability to share additional attributes into FRR and then have them distributed. So what this model does is the entire, essentially the full set of the GPU IP addresses. I was just showing a couple of examples here. That entire set of IP plus MAC plus system port can be completely distributed through IBGP. And once every entity learns about these, now the GPU to GPU communication is established in a completely distributed way. And as I mentioned, a few of the simplifications that we talked about in the earlier slides does come handy here because there is really no need for distributing any neighbors. There are no external prefixes that are pointing to a neighbors. There is no need to distribute any lag membership. So there's literally the system port piece is the only one, only attribute extension that is needed to the EVPN route type 2. For managing, for essentially establishing all of the required connectivity here. So that, I think, brings me to the last one. I mean, it's not really call to action, but it's essentially call to the community. The goal would be to, like, we're working on a HLD to bring this to the community and work with all the other partners to make sure that we pick up the right design option for SONiC to get into the distributed schedule fabric model. And as I said, I just want to reiterate that, while the MLAI, the backend MLAI network use cases seem to be the use case of the day, we believe there are more use cases that would come up that could leverage this architecture in the future. Right, that's all I had. Thank you. I know we might have some time for a few questions.
Yeah, thank you, Praveen. Sure. We have time for 2 questions. Anyone online have questions? Can you help to check?
Hi, I'm Saad from Dell. Just a question in terms of just you mentioned now MLAI use cases, right? Because the way you explained is more about that scheduler and middle layer, still solving out the routing issue, reducing the prefixes and other dependencies. So I just need to understand more context because, as you know, MLAI is based on data, right? So how you plan to like expose it in a way, and what are some sort of initial or first use cases that you are looking forward to?
Yeah, so it's a good question. So actually, I did not go into the details of how the scheduled fabric, the scheduled fabric itself helps the distributed MLAI workloads and what are the characteristics of those workloads. So as I mentioned, I was just providing a reference to a couple of talks that were given during the OCP summit in October, which actually go into the details of what are the characteristics of those those traffic parameters for those use cases. But I'll just quickly touch upon that. So the main thing there is, unlike the traditional data center fabric traffic patterns, the key to the backend ML workloads is that there are very, very few flows because you're essentially running the workloads distributed or the job gets distributed across a set of compute elements. And then as those compute elements are computing, each GPU is computing portion of that job and then exchanging the intermediate data with the next entity in the sequence. The traffic flows are few, but they are all elephant flows. So you could have flows that are up to the NIC's throughput, whether it's 100 gig or 200 gig. So that's where traditional ECMP actually fails. And that's where mechanisms like scheduled fabric or Ethernet with additional enhancements like HPCC plus or adaptive routing, those come into play. Right. So I know I didn't get into those details, but I would strongly suggest to go through the OCP talks, and if there are, obviously we'll bring this to the community and we should have further discussion on that. I hope I answer your question.
This distributed Redis database for the chassis DB is interesting. So in that case, we need some kind of WIP so that other devices could reach it through that WIP, right?
So Redis cluster already supports that, Guhan. So you could actually define either using a Redis Sentinel or Redis cluster does allow the ability to define a cluster with a common IP, and the cluster itself manages which is active and which entity is going to be active.
So that part I get, but I mean the WIP we need to distribute across the fabric so other ones knows how to reach that common IP, right?
The WIP will have to be known to each of the leaf instances, correct, or each of the TARs. Yeah, exactly.
Thank you, Praveen.
Quick question, sorry.
Oh, sorry.
Any other questions?
Yeah, sorry. This is Jalal. I'm online from Northern Canada. I have a different sort of perspective on SONiC because the application that I'm working on is a very different application. It's within the 5G SA core control plane and data plane environment. So what we are trying to do is we are trying to implement service function chaining, hosting our processing intensive workloads on IPUs or DPUs, and then basically establishing connectivity between these processor intensive compute hosted endpoints with the UPF. So we're trying to employ segment routing over V6 data plane. So I was wondering if SONiC can support such a construct. We have considered FRR. We are also deeply involved with NVIDIA, looking at their FRR routing daemon implementation as well. But most implementations that we have seen do seem to lack the capability of segment routing support. So is that on the roadmap perhaps, or is that something you can comment on?
So I don't know if the question was specific to the scheduled fabric or more on the SRv6 part, which was the earlier presentation. But if your question is related to the scheduled fabric, I think it's a good use case to have a conversation offline with respect to what are the traffic patterns and how would the scheduled fabric based model and then thereby SONiC can help those use cases. Yeah, I think we should definitely take that offline.
Fantastic.
If you need more information, Jay, please contact me. We have added SRv6 in SONiC, and we have more that we will be adding in the near future. We have just added microSID this year as well. I'm Reshma Sudarshan from Intel, so we can chat offline too.
Sure, fantastic. If you don't mind sharing your contact details in the chat window here in Zoom, and also the link to the recorded sessions, that'd be great. Thanks.
Thanks,
Thanks, everyone.
Praveen. Yeah. Next one.